Happy Pi Day 3.14, March 14th. They tell you that pi is an irrational number. So what is an irrational number? First, let's define what a rational number is. A rational number is a number that can be written as a fraction, or more precisely as the ratio of two integers. An integer in the numerator divided by an integer in the denominator. When you divide them out, you get some number. So that's the definition of a rational number. Pythagoras, the ancient Greek Pythagoras, he thought that all numbers were rational. And then he was really pissed off when they found out that the square root of 2 is irrational. So irrational means it's not rational, which means you cannot write it as the ratio of two integers. And some numbers are like that. Like it's easy to prove that the square root of 2 is irrational. Pi is also irrational. It means you can't write it as the ratio of two integers. But on the computer, using double precision floating point arithmetic, pi is in fact rational, and I will produce the integer numerator and the integer denominator such that when you divide them, you get pi on the computer. Because the catch is, an irrational number, if you write out the decimal digits, it goes on forever. That's why they say like pi goes on forever. The digits just keep going and going and going. But the double precision floating point arithmetic only stores 16 decimal digits. So you only get 16 digits. So once you have a 16-digit number, it's actually 53 binary digits, it's easier to think of decimal digits. So once you have these 53 binary digits, you just convert that into an integer in the numerator and the denominator, and you divide them out and you get pi on the computer. So that's the whole point of this day. I will show you, I'll do it in Python. I'll have this number divided by this number equals math.pi, and it returns true. And I'll print them out and print their digits out, and you'll see that on the computer, pi is rational. Now, don't go saying to your math teacher that pi is rational, because it's more of like a abstract intellectual exercise, I guess, that pi is irrational. But from a practical point of view, like on the computer can't store irrational numbers exactly in finite precision floating point arithmetic. And here's a look at the details. Okay, so I claimed that pi was rational on a computer using double precision floating point arithmetic. And here is my proof. This number, 884 trillion, blah, 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 divided by 281 trillion. So these are two integers. We divide them out and we say, does that equal math.pi? This is in Python. And boom, it returns true. So this first line, I'm printing out what is math.pi, and this is in fact only correct to 15 digits. 323. Yeah, so this is not right. This should be 8979323. So these digits are wrong here because the computer only knows 16 decimal digits of pi. But that's what it thinks it is. And anyways, so that's what this first line is printing out what the computer thinks pi is. The second line is printing out the ratio of these two integers, we're printing out 27 digits, even though it's only accurate up to 16 digits. And then here's the bottom line. Here's the punchline. Does math.pi equal the ratio of these two integers? And it says yes. So here, let me evaluate this cell. I didn't just like Photoshop this thing here. Here, look, let me change this digit to a 7. Let's see. It returns false. Let me change this to a 6. Because I could have just, this whole thing could be fake. I could have easily enough faked this whole thing in my own Python interpreter or anything else. But go ahead and check it for yourself. Divide these two numbers out in Python and you'll see. My intent is not to fool you. My intent is to expose the rationality of pi. But in fact, what I'm saying, there's not much content to what I'm saying because you simply can't do any irrational number exactly in finite precision. So that's all I'm saying. But the cool thing is I've actually produced the two numbers that give you pi. So this is a nice rational approximation to pi, which is good to 16 decimal digits, and in fact that's how the computer represents pi. So that's the bottom line. That's your Happy Pi Day video. I can show you some details if you like Python and you like math. So here's how I started. I know this many digits of pi. This is what I know off the top of my head. So I type that in. So I'm just printing that out, and then I'm printing out. This first line is just printing the string. This is correct to 27 digits. This next line is converting that number to a floating point. See how it disagrees. I'm just making this a float, and it already disagrees in these digits, and this is what the third line is what the computer thinks math.pi is. So because you can only get 16 decimal digits, we see that it's good for the first 16 digits, and then it's wrong after that. And so basically I just wrote a little function. If you give the fractional part of an integer, I wrote this little function to get the binary digits. So I just got, the 52 binary digits of pi. And then once you have the binary digits, you can form an integer out of that by just, finding the least common denominator and multiplying through. So you get this numerator. So this numerator here gives you the numerator of the fraction, and then the denominator is just 2 to the n. And you can just do a little GCD to simplify that guy. GCD is greatest common divisor to put the fraction in lowest terms, and blah, blah, blah. That's what I did. That's what this loop here is. These are rational approximations to pi using binary digits, using 4 binary digits, 5, 6, 7, all the way up to 52 binary digits. So here, that's what the table is here, using 4 binary digits and 5 binary digits, 6, 7, 8. So we keep adding more and more binary digits. So these are rational approximations to pi. Keep going down, 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 and we go all the way down here. So at 53 binary digits, we get this thing. This number wrapped around and divided by the denominator, and I went a little bit past that, and you see that it stays the same. So here is your rational approximation to pi. That is what the computer is using. And here's your proof. I say, does pi equal the ratio of these two integers? And it says yes. And this is kind of funny. Like, to a pure mathematician, your mind explodes when you see this, because pi cannot be written as a ratio of two numbers, but it's only comparing. When it does this comparison, it's making a floating point number out of this and making a floating point number out of this, and saying, do the first 16 digits agree? And this is saying yes, they do. So computers, finite precision floating point arithmetic, you cannot store an irrational number exactly. And happy Pi Day to you. I hope you had the greatest Pi Day of your life, and I hope every day is better than the next. And go tell your teacher to type this in on their computer and test whether it equals pi, and see what they have to say for themselves. And thank you very much. Have a good year.